We are now going to look at example 2 in section 8.4. So example 2 revisits the series we met in example 1, but we're going to actually show a proof that this series converges. So in example 1 in the previous video, we talked through why it should converge, and then we looked at the theorem that shows it. But how would we actually create that argument or proof that showed that this series converges? All right, so what we're going to do is start with some scratch work, just like we saw in the last section. So what's our scratch work? So here in our scratch work, we want to set ourselves up to be able to justify the claims in that theorem, or the assumptions rather in that theorem, and then we can conclude the claim. So let's just take a look at what we have. So first we want to make sure that we communicate or show that that series we were given, -1 to the n minus 1 over n, is in fact alternating. So we want to rewrite it in the alternating series form of the alternating series theorem. So we need to write it as a sum of -1 to the n minus 1 in our case times some bn term. So for us, that would be 1 over n. So here, this shows that we do have an alternating series, meaning our series, since we are able to show equality here, does have the form of an alternating series. In particular, we have the bn term is equal to 1 over n. So now we need to check those two conditions of the alternating series theorem. So that is condition A. We need to check that the limit as n goes to infinity of 1 over n is equal to 0. And yes, we have that. That is true. Check. B, we need to check that the nth plus 1 term, so b sub n plus 1 is less than or equal to b sub n. So that would mean 1 over n plus 1 is less than or equal to 1 over n. Check, that is also true. So now we have that our series is alternating and that our series satisfies those two conditions of the alternating series test. So we're going to be good to go to write our proof. So what does that look like? Well, I'm going to set up here proof. So since our series is an alternating series, and we have the conditions, those conditions A and B. So those are the conditions that the limit as n goes to infinity of 1 over n equals 0, and 1 over n plus 1 is less than or equal to 1 over n. That's true for all n. Then, or rather this means, so since our series is an alternating series and we have the conditions limit equals 0 and this inequality for our all n, you can say so the given series converges by the alternating series test. And so we can check that we're using all of those properties required in a proof. So we're using complete sentences? Yes. Are we using the assumptions in the theorem and showing that our series satisfies those assumptions or conditions? Yep. And are we stating the theorem that we're using to make our conclusion? Alternating series test? Yes. And we have our conclusion that the series converges. Okay, so what more can we say about this theorem? Well, let's look at part B that asks us to approximate that infinite sum value. So we know that it converges. So in part B, we're asked to use the first 4 terms to approximate the infinite sum given in that example 1 and example 2. What is the maximum possible error in your approximation? So we're going to approximate what this sum is equal to. So we have our series n equals 1 to infinity of -1 to the n minus 1 over n. And again, that's equal to 1 minus 1/2 plus 1/3. I'm going to go ahead and write out some of those terms so we can see what it is they're wanting us to approximate. Okay, so we're just going to use the first 4 terms to approximate this sum. So that would mean we're going to add up these first 4 terms. So just looking at these first 4 terms, go right here. So that would be S sub 4. So it's going to be equal to 1 minus 1/2 plus 1/3 minus 1/4. So now we can get out our calculator and we can compute that as around 0.583. And so now the second part, so that's our approximation of the sum. The second part says, what is the maximum possible error in your approximation? Well, recall from that alternating series approximation theorem, we know that if we use the S sub n partial sum to approximate our value, we're going to be within the nth plus 1 term. So that means this nth plus 1 term here, 1/5, is going to be an upper bound for the error in our approximation. So let's go ahead and write that out. So the approximate sum of the series is 0.583. So this is an estimate. So it's not exact, but it's an estimate that we're using. And now by that alternating series estimation theorem, so we can write that out by the alternating series estimation theorem. We know how close we are. Not exactly, but we know at least kind of a maximum of how far away we are. We know the maximum error in this approximation is given by B sub 5, which is equal to 1/5, which is 0.2. And so just to recall how we're seeing that. So the actual value of our theorem or of our series is S. Actual value. We are using S minus 5 to approximate it. So what is that error? How far away are we? That error is computed by subtracting the actual value minus our value. We know that error is going to be less than or equal to, in this case, B sub, oops, changes a little bit. We were using S sub 4, so this error is going to be less than or equal to B sub 5. So that's all we're using here. We're just unpacking and using that alternating series estimation theorem. All right, very cool. Well, great work going through this example.